The topic for this video is the following: quantum optimization, mathematical modeling, algorithms, Python programming, and applications. What is the future of operations research? Quantum optimization will play a crucial role in the future transformation process of the world and mankind. Operations research, OR, has long been a cornerstone of decision-making processes, optimizing complex systems and solving intricate problems. As we venture into the future, the landscape of operations research is poised for a substantial transformation with the emergence of quantum optimization. This video explores the profound impact of quantum optimization on the future of operations research, delving into its mathematical foundations, algorithmic advancements, Python programming integration, and applications. Limitations of classical optimization models and quantum optimization. The drawbacks of classical optimization models lie in their limitations in solving complex real-world problems. Classical algorithms often face challenges in handling large-scale combinatorial optimization and dynamic systems. Quantum optimization modeling promises to overcome classical limitations. Leveraging principles from quantum mechanics, they explore multiple solutions simultaneously, enabling more efficient searches through solution spaces. Mathematical foundations and methods of quantum optimization. The mathematical foundations and methods of quantum optimization represent a fascinating intersection of quantum mechanics and mathematical optimization theory. At the heart of quantum optimization lies the mathematical framework of quantum mechanics, a branch of physics that describes the behavior of matter and energy at the smallest scales. Linear algebra plays a crucial role in expressing and manipulating quantum states and operations. The mathematical concepts employed in quantum optimization algorithms include the use of qubits, quantum gates, entanglement, and quantum annealing. Harnessing quantum states and entanglement is a key strategy in designing quantum optimization algorithms. Different quantum optimization algorithms. There are several algorithms for solving quantum optimization problems which are discussed below. Quantum optimization algorithms aim to harness the principles of quantum mechanics to solve optimization problems more efficiently than classical counterparts constrained by the NP-hard problems in these models using different algorithms. One of the prominent quantum optimization algorithms is the quantum approximate optimization algorithm, QAOA. QAOA employs a variational approach, combining classical and quantum components to find near-optimal solutions to combinatorial optimization problems. Another noteworthy algorithm is the quantum annealing (QA) approach. Quantum annealers, such as those developed by D-Wave systems, utilize quantum tunneling to search for optimal solutions in a problem solution space. Grover's algorithm, originally designed for searching an unsorted database, also exhibits optimization capabilities. Grover's algorithm can be adapted to serve optimization tasks by encoding problem constraints into a search space. Recently, variational quantum eigensolver, VQE, optimizes a quantum circuit's parameters to find a given Hamiltonian's ground state energy. As algorithms like QAOA, quantum annealing, Grover's algorithm, and VQE mature, they hold the potential to transform industries by solving complex optimization problems more efficiently than their classical counterparts. Comparative analysis of different quantum optimization algorithms. Each approach has strengths and limitations. AQC and quantum annealing excel in finding global minima, while VQE is versatile but computationally intensive. Grover's algorithm, though powerful, is specific to certain problems. Using Python programming in quantum optimization. Python, a versatile and widely used programming language, plays a pivotal role in harnessing the potential of quantum optimization due to its flexibility, extensive libraries, and vibrant community. One of the most notable libraries is Qiskit, an open-source framework developed by IBM for quantum computing. Qiskit allows researchers and developers to create, simulate, and execute quantum circuits on real quantum processors or high-performance simulators. Hybrid quantum classical optimization approach. Python's versatility extends to hybrid quantum classical optimization techniques. Python allows the seamless integration of classical optimization algorithms with quantum subroutines, creating hybrid solutions that leverage the strengths of both classical and quantum computing. Computational and modeling benefits of quantum optimization. Quantum algorithms significantly reduce computation time for complex optimization problems. Quantum optimization offers unparalleled accuracy, crucial for real-life applications. Benefits in real-life applications of quantum computing and quantum optimization. Quantum optimization's impact extends to real-world scenarios. From logistics and finance to healthcare, we explore how quantum approaches enhance decision-making processes, leading to more optimal and resource-efficient outcomes. Applications of quantum optimization in the real-world environments. As quantum optimization has emerged as a groundbreaking field with diverse applications across various domains, this video reviews the multifaceted landscape of quantum optimization, highlighting its significance in fields such as artificial intelligence, logistics, finance, and cryptography. In the realm of artificial intelligence, quantum optimization algorithms offer a promising avenue to enhance machine learning models. Quantum computers, with their inherent parallelism and ability to process complex data sets more efficiently than classical counterparts, can transform optimization problems central to machine learning. Quantum algorithms can efficiently address combinatorial optimization challenges, aiding in the optimal allocation of resources, minimizing transportation costs, and streamlining supply chain operations. In the financial sector, quantum optimization can profoundly change portfolio optimization and risk management. This can lead to more accurate risk assessment, improved investment strategies, and enhanced financial decision-making. Quantum-resistant cryptographic algorithms are being developed using optimization techniques to ensure the security of information in a post-quantum computing era. Beyond these specific applications, the overarching impact of quantum optimization extends to addressing NP-hard problems across diverse disciplines. The future of operations research appears promising with the advent of quantum optimization. As quantum computing technology continues to mature, the synergy between quantum optimization and operations research is poised to redefine how organizations approach decision-making and resource allocation in the coming years. Therefore, quantum optimization will play a crucial role in tremendously shaping the world's and mankind's future development. The operations research community should embrace this new operations research. Thanks for watching.